Unit 5, Stoich Point Review. You can access this review and this video at srhschem.wikispaces.com. Let's begin with solutions. The first question asks us to use polarity to explain why compounds such as sugar and salt will dissolve in water, but oil will not. So first, we need to look at the actual structure of the water molecule. Oxygen has 6 valence electrons and each hydrogen has 1. So when we put them all together, we get a full octet. So we see 8 electrons surrounding the central oxygen atom. Oxygen is more electronegative than hydrogen, meaning that it pulls harder on the electrons in the shared covalent bond. So the electrons that are being shared in the covalent bond here, they're actually going to be pulled towards oxygen. And since they spend more time around the oxygen, that gives the oxygen a partially negative charge, while the hydrogen has a partially positive charge. So this means we can think of a water molecule as a little tiny magnet with a positive end and a negative end. If we look at something like salt, sodium chloride, salt is actually made of positive and negative ions. And if we look at something like a glucose molecule, that's sugar, that molecule has a lot of charged groups on it. So both of these have charges, thus they can dissolve in a charged solvent such as water. So whenever water is coming into contact with either of these, the charged ends of water are ripping apart these charges, so they will dissolve. If you look at something like oil, so here is pentane, which is just a hydrocarbon like oil. This doesn't have any charges, so it cannot interact with water. It cannot dissolve in water. This is summarized by the term like dissolves like. Something that is charged will only dissolve in something else that is charged. Something that is not charged will only dissolve in something else that is not charged. The next question asks us to predict if each of the following will or will not conduct and explain why. So in order to conduct, there are 2 conditions. Number 1, we must have ions. We must have charged particles present in the solution in order to conduct. And number 2, those ions must be able to move. So our first beaker is just water. There's nothing in it, so it doesn't have any ions. Therefore, it will not conduct. In our next beaker, we have ions, but they're stuck together as a solid. So since they cannot move, this will not conduct. In the third beaker, the ions have dissolved in water and now they are able to freely move. Thus they can carry the electric charge. And in the last beaker, we have glucose. Glucose is charged, but it doesn't have ions. Therefore, this will not conduct. Now let's look at the properties of solutions, suspensions, and colloids. So the first thing that you should keep in mind is the relative particle size. So if a solution was the particle size of a marble, the particle size of a colloid would be like a softball, and the particle size of a suspension would be like a basketball. So an example of a solution would be food dye in water. So my particle size is going to be very small. We're talking about atoms or ions, so very small particles. And those could just be atoms or ions. Settling over time. So if you let a solution like food dye sit, the food dye particles are not going to all sink to the bottom. And that's because those particles are so small that they're actually supported and held up by the water. So it does not settle over time. Filtering through filter paper. So if you look at filter paper versus a membrane, filtering paper is going to have bigger holes than a fine membrane. So solution particles are very, very small, which means that they can pass through both. So because the particle size is so small, kind of like a pasta strainer, it catches the things that are too big to go through the holes. So the holes of the filter paper and the holes in the membrane are bigger than the solution particles. Last is scattering of light. So this is the Tyndall effect. And the Tyndall effect is just the scattering of light by particles. And the bigger those particles are, the more light they scatter. So in the case of a solution, the particles are very, very small, so they do not scatter light. Next up is a colloid. So an example of a colloid would be milk. So the particle size here is going to be small, but it's going to be something like molecules. So many atoms stuck together. So still pretty small, but we're bigger than the particle size for solution. Colloid, the particles are still very small, so they can be supported by the solvent, so they will not settle over time. For a filter paper versus a membrane, the colloid particles are smaller than the filter paper holes, so they will pass through, but they are larger than the membrane holes, so they do not pass through. For scattering of light, again, the bigger the particles, the more light they scatter, and since colloid particles are larger than solution particles, they will scatter light. Last is a suspension. So these are going to be large molecules or aggregates, so larger than colloid particles. Because they are such large particles, big heavy particles are going to tend to sink to the bottom of the suspension, so they do settle over time. So you can think of muddy water. If you leave muddy water sitting on the table, eventually all the mud and the dirt settle to the bottom. Filtering through filter paper and fine membrane. These molecules are so big that they are bigger than the holes in the filter paper and in the membrane, so they do not pass through. Particles are too big. So it's kind of like whenever you use your pasta colander and you strain out the water, the pasta particles or the pasta pieces are too big to go through the holes. Same thing for suspension particles. And scattering of light, of course, is going to be yes, because these big, large particles can scatter lots of light. Now let's take a look at the solubility curves. So on this table, on the y-axis, we have solute per 100 grams of water. So what this is saying is if I have 100 grams of water, and how much of each different solute can I dissolve in it? Along the x-axis, we have temperature. So why do SO2, NH3, and HCl show a negative slope? These are all gases, and gases become less soluble as temperature rises. So we have a negative slope because the hotter the solution is, the less the gas is going to stay in the solution. So for solids, we see the opposite relationship. We all know that if we want to make tea, we dissolve the sugar while it's hot because solids are more soluble in warm solvents. For gases, it's just the opposite relationship. How much NaCl can dissolve in a 200 gram sample of H2O at 90 degrees Celsius? So first thing we got to figure out is if we have 100 grams, how much can we dissolve? So let's go ahead and find the NaCl curve. So here it is. And I recommend on your test, just like I'm doing here, that you highlight. You don't want to get a question wrong simply because you're looking at the wrong line. So at 90 degrees, we can dissolve 40 grams. So that's how much I can dissolve in 100 grams. If I had 200 grams, it's just going to be twice what I could in 100 grams. So 40 times 2 is going to give me 80 grams. So if I take 200 grams of water and I heat it to 90 degrees, the most salt I can possibly dissolve in there is going to be 80 grams. The only way I could get more would be to continue to heat the water. Now, if I put less than 80 grams, so if I put 75 grams, I could still dissolve more salt at that point. That solution would be unsaturated. 80 grams is the maximum amount. that is saturated, and if I do something to the water, like heat it further, I could get it to dissolve more salt. That would be supersaturated. Okay, a saturated solution of KCl is made at 80 degrees Celsius. If the solution cools to 10 degrees Celsius, how much KCl will precipitate? So that is a fancy word for fall out of solution. So just like before, first thing we're going to do, we're going to highlight the correct line so we don't get confused. So first thing I got to figure out is how much would dissolve at 80. So here's 80, follow my line up. I'm at about 52. Now I got to look and do the same thing for whenever it is at 10 degrees Celsius. So at 10 degrees Celsius, looks like 30. So if at 80 degrees I can hold 52, and at 10 degrees I can only hold 30, I got to subtract to get the difference. So if I cool from 80 to 10, 22 grams of KCl will fall out of solution. Now let's look at some molarity calculations. A solution is made with 150 grams of sodium chloride in 800 milliliters of water. Calculate the molarity. So the formula for molarity is that molarity equals moles over liters. So let's look at what we are given. Originally we're given 150 grams of NaCl. So I need to convert that first into moles. So now we want to convert this into moles. So gram needs to go on bottom, and mole needs to go on top. So anytime you see grams and moles, that's molar mass. The molar mass of salt is 58.44 grams in 1 mole. So whenever you solve this, you get 2.57 mole. We also aren't given liters, we're given milliliters, so there's another conversion. I'm just going to take 800 milliliters and convert milliliters into liters. 1 liter is 1,000 milliliters, so I've got 0.8 liters. Now I just got to divide the two. And that's going to give me a molarity of 3.21. So molarity is always just moles on top of liters. You might have to do some conversions to get moles and liters. So in this case, we had to convert grams to moles and milliliters to liters. But either way, it's still moles on top of liters. The next question, how many moles of HCl are present in a 10 milliliter sample of 6 molar hydrochloric acid? So once again, we need our equation. This time, we're solving for moles. So I'm given molarity, and I'm given milliliters, and I want to solve for how many moles. So first thing I need to do is convert my 10 milliliters into liters. So I know that there is 1,000 milliliters in 1 liter. So that means that 10 milliliters is 0.01 liters. Okay, now I need to solve for moles. So I know that my molarity is 6. I'm solving for moles, and I'm dividing by 0.01 liters. So I need to get the x by itself, which means multiply both sides by 0.01. So I'm going to do that on both sides. And that gives me x is equal to 0.06 moles. So again, it's just moles and liters. There's 3 possible variables here, molarity, liters, moles. As long as you have 2 of them, you should be able to solve for the third, keeping in mind that you might have to do a conversion. Now let's look at some mole conversions and stoichiometry. So first, consider this equation. So in stoichiometry, you always need a balanced equation. This equation is obviously not balanced, so let's do it. First thing that we have is calcium. Then we have chloride, sodium, and then I have PO4. If you look on both sides of the arrow, we see PO4 stays intact, so we're just going to keep PO4 together as one polyatomic ion. So let's count. Calcium, I've got 1. Chloride, I've got 2. 3 sodiums, 1 PO4. On the other side, 3 calcium, 1 chlorine, 1 sodium, 2 phosphate. So to me, the first thing I want to take care of would be calcium. So I'm going to put a 3 over here. So this gives me 3 and 6. Okay, now in order to fix this, put a 6 over here. And now my sodium's not balanced, so if I put a 2, and now my equation's balanced. This one right here, we just assume that there is a 1. All right, now that we're balanced, we can do some stoichiometry. So, how many moles of CaCl2 are needed to produce 18 moles of NaCl? So, in this case, I was given 18 mole of NaCl, which means I don't need this box. I was also asked for how many moles of calcium chloride. So, not going to need this box either. So I'm just going to go from 18 moles of sodium chloride. I just want to convert this using a mole ratio. So mole of NaCl goes on bottom, and mole of what I'm looking for goes on top. Okay, so according to my balanced equation, there are 3 moles of CaCl2 for every 6 moles of sodium chloride. So mole of sodium chloride cancels mole of sodium chloride, so that means that my answer is going to be 9 moles of calcium chloride. All right. Next problem, how many moles of Na3PO4 are needed to completely react with 3 moles of calcium chloride? So this time my given is 3 mole calcium chloride, and my wanted is how many moles of Na3PO4. So I don't need these boxes, don't have to do any conversions, I'm just going to use mole ratio. So I've got 3 mole of calcium chloride over 1, and I want to convert this, put mole calcium chloride on bottom. I want to convert this to moles of Na3PO4. So that's just a mole ratio. So according to my balanced equation, for every 2 moles of sodium phosphate, there are 3 moles of calcium chloride. So calcium chloride cancels calcium chloride, and I've got 3 on top of 3. That cancels out, so my answer is 2 mole Na3PO4. Now, if you were clever, you saw that I was asking about 3 moles of calcium chloride, how many moles of Na3PO4? Well, in the balanced equation, it already has 3 moles of CaCl2. Therefore, it must be 2 moles of Na3PO4. So it's possible to solve this problem just based on inspection. Now let's look at neutralizing some excess acid. So if Miss L made 2.5 moles of extra acid, how many moles of calcium hydroxide does she need to neutralize it? So in this case, we are given 2.5 mole of the acid, so that's HCl. And I want to know how many mole of calcium hydroxide do I need. So that means I don't need these boxes because I'm not given liters, grams, or particles. I'm given moles. So once again, this is just a mole ratio problem. So if there's 2.5 moles of HCl, I want to know how many moles of calcium hydroxide. So I'm canceling out moles of HCl. I'm putting moles of calcium hydroxide on top. So this is mole on top of mole, which is just a mole ratio. So according to the mole ratio, 1 mole of calcium hydroxide for every 2 moles of hydrochloric acid. So hydrochloric acid cancels. So my answer is going to be 1.25 mole of calcium hydroxide. Next, if I use 10 grams of calcium hydroxide, how many moles is this? So we're starting with 10 grams, and I need to go to moles. So this is just going to be a simple conversion. 10 grams calcium hydroxide. I'm going to convert this into moles. So 1 mole of calcium hydroxide. Going to need my molar mass. So 1 mole of calcium hydroxide weighs 74.09 grams. So grams cancels grams. So my answer is going to be 0.13 mole CaOH2. In this reaction, the limiting reactant is 2.5 moles of HCl. What is the theoretical yield of calcium chloride? So in this case, I'm given 2.5 mole of HCl. And I want to know what the theoretical yield of CaCl2 are. So don't need this first box. So first I'm going to take my 2.5 moles of HCl, and I need to convert this using a mole ratio into the moles of what I want. So I need to convert this into mole of calcium chloride. Now I want to convert moles of calcium chloride into grams of calcium chloride. So mole on top of mole, that is the mole ratio. So there's 1 mole of calcium chloride for every 2 moles of hydrochloric acid. And then I'm going to need the molar mass for calcium chloride. So that is 110.98. And whenever I solve, mole HCl cancels mole HCl, mole CaCl2 cancels mole CaCl2. So my answer is going to be 138.73 grams of calcium chloride. So that is the maximum amount I can make, assuming that I start with 2.5 moles of HCl, and that is the limiting reactant. Next, why is it important to know the limiting reactant in a reaction? So several reasons. It allows you to predict how much product you can make. So if you're trying to make a certain amount, you know exactly how much to start with. You can also use this to determine percent yield, so how good was your recovery of the product during the experiment. And you also can try to make the most expensive reactant the limiting reactant. This way you don't waste any. So now we are looking at hydrochloric acid reacting with baking soda. A student mixes 5 grams of baking soda with 20.5 milliliters of 3 molar hydrochloric acid. What is the limiting reactant? So in this case, we're going to do 2 calculations. If I have 5 grams of baking soda, how much salt can I make? I picked a product, I picked salt. Then I'm going to say if I have 2.5 milliliters of 3 molar hydrochloric acid, how much salt could I make? So we're doing two calculations here. So let's do the first one. If I have 5 grams of baking soda, in stoichiometry, whatever you are given, convert it into moles. At this point, I want to convert moles of baking soda, so that's going to go on bottom to cancel. Convert moles of baking soda into moles of salt. And I'm going to go ahead and convert moles of salt into grams of salt. Okay, so first I've got mole and gram, so that's molar mass. So the molar mass of baking soda, 1 mole, weighs 84.01 grams. And now I've got mole on top of mole, which is a mole ratio. So 1 mole of HCl for every 1 mole of baking soda. And now I need the molar mass of NaCl. That's 58.44. So if I solve, grams cancels grams, moles, 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 moles. So my answer is going to be 3.48 grams of sodium chloride. All right, so I've done one of my calculations. If I start with 5 grams of NaHCO3, I can make 3.48 grams of NaCl. Now I need to do my second calculation. So this time I start out with 20.5 milliliters of 3 molar hydrochloric acid. So you're given the volume and the concentration. So that should be a big hint to you that you're going to need to use the molarity equation. So molarity is moles per liter. In this case, my molarity is 3, and I have 20 milliliters, so I need to convert 20 milliliters into liters. So 1 liter is 1,000 milliliters, and that's going to give me 0.0205 liters. Okay, so molarity is 3. I'm looking for how many moles, and I've got this many liters. So whenever I solve for x, I'm going to get the number of moles as 0.0615 mole. Okay, so for my second calculation, I'm starting out with 0.0615 mole of HCl, and I want to convert moles of HCl into moles of salt, my chosen product, and then I want to convert moles of NaCl into grams of NaCl. So I've got mole on top of mole. That's a mole ratio, 1 to 1. I know that 1 mole of salt is 58.44 grams. So whenever I plug this all into my calculator and solve, I'm going to get 3.59 grams of salt. So we did two calculations. If I have 5 grams of baking soda, how much salt can I make? If I have 20.5 milliliters of 3 molar hydrochloric acid, how much salt can I make? The one that makes less is your limiting reactant. So my limiting reactant in this case is going to be the 5 grams of baking soda. I will run out of this first. Next, what is the theoretical yield of NaCl? So it is the maximum amount of salt that I can possibly make. and it depends on the starting ingredients. So my limiting reactant was the 5 grams of baking soda, and the maximum amount of salt that I can make from that is 3.48 grams of NaCl. So theoretical yield is based on calculations. So remember, whenever you calculate for something, you're assuming everything's going to go right. So that's the theoretical maximum amount that you could make. But of course, in an actual experiment, there's always error. So the next question says, if the student actually obtains 3.2 grams of NaCl, what is the percent yield? So we're going to need our equation. So this is kind of like if you were taking a quiz and the maximum points that you could have gotten on this quiz, the maximum yield of sodium chloride, was 3.48. But on this quiz, you only scored 3.2. So you take the part that you got, 3.2, over the total that you could have gotten, and multiply by 100%, and that's going to give us a percent yield of 91.95%. So in this experiment, the students did pretty well. They got most of the salt that they could have gotten, and a pretty high percent yield. Next one is asking about molar mass. So how do you find it and what are the units? So you just have to add up the molar masses from each element on the periodic table. So look at your chemical formula and you might have to double or triple or multiply by whatever number based on how many atoms there are of each element. And you add up that sum and that gives you the molar mass for that element. The units of this are grams per mole. So this is what you can think of. If you were trying to find the molar mass of sodium chloride, you would count out a mole of sodium chloride atoms. So you would sit and count out 6.02 times 10 to the 23rd molecules of sodium chloride. And you would then put that on a scale. And that mass would be the molar mass. So it is the mass in grams of 1 mole of the compound. Number 5, you have 30 liters of O2 gas. How many particles, grams, and moles is this? So, for the first one, we're going to start at particles. We're going to go to moles. So for the first one, we are given 30 liters. We want to get to particles. So we got to take liters to moles, and then moles to particles. So I've got 30 liters of O2, and I want to convert this first into moles. So we need to know the conversion factor. Then I want to convert moles into particles. So I just got to know the conversion factors. So moles and liters, the conversion factor is 1 mole is 22.4 liters, and 1 mole is 6.02 times 10 to the 23rd particles. So whenever we solve this, liters cancels liters, mole cancels moles. So my answer is going to be 8.06 times 10 to the 23rd particles. So the next problem is if I have 30 liters of gas, how many grams is this? So we're going to take liters, convert it to moles, moles, convert it to grams. So I'm starting with 30 liters of O2, and I want to convert this to moles. So 1 mole we just said was 22.4 liters. And now I want to take moles and change it into grams. So this is the molar mass of oxygen, O2. So 1 mole of O2 weighs 32 grams. So whenever we solve this, liters cancels liters, moles cancels moles. So my answer is going to be 42.86 grams. The last calculation is only a one-step calculation. And you've already done the calculation twice. I just want to take liters and convert it to moles, and then I'm done. So I've got 30 liters of O2, and I want to convert liters into moles. So liter would cancel liter. So my answer is going to be 1.34 moles of oxygen. So to do the first one, we took liters to moles to particles. The second one, liters to moles to grams. And the last one was just liters to moles. So that is the end of this review. Again, you can find this on srhschem.wikispaces.com.